Conservation of momentum. The impulse momentum theorem was derived from Newton's second law and is really just an alternative way of looking at single particle dynamics. To discover the real power of momentum for problem solving, we need also to invoke Newton's third law, which will lead us to one of the most important principles in physics, conservation of momentum. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. The following figure shows an isolated system of two particles before and after they collide. By isolated, we mean that no external forces, such as the gravitational force or friction, act on the system. We assume the only forces during the collision as the objects are interacting are the action-reaction pair. Newton's third law states that at all times these two forces are equal in magnitude and opposite in direction. The forces act between the two objects for a given amount of time. Regardless of how long the time is, it can be said that the time that the force acts upon object A is equal to the time that the force acts upon object B. Since the forces between the two objects are equal in magnitude and opposite in direction, and since the times for which these forces act are equal, it follows that the impulse experienced by the two objects are also equal in magnitude and opposite in direction. The impulse is equivalent to change in momentum. This equation can be rearranged to give the following important result. This equation is the law of conservation of momentum. In words, this equation says that for an isolated system, the total momentum of objects before collision equals to the total momentum of objects after collision. This result is called the law of conservation of linear momentum. The law of conservation of momentum can be stated as follows. When no net external force acts on a system, the total momentum of the system remains constant in time. A 75 kg hunter in a stationary kayak throws a 0.77 kg harpoon at 50 meters per second. The mass of the kayak is 10 kilograms. What will be the velocity of the kayak and hunter immediately after the harpoon is released? First of all, let's define the system to be hunter, kayak, and harpoon. We assume this is an isolated system. The hunter, kayak, and harpoon each have an initial velocity of 0, so the initial momentum is 0. After the harpoon is launched, the hunter and kayak move together as a unit, so they have the same final velocity. We apply the law of conservation of momentum by equating the initial momentum and the final momentum. The velocity of the kayak and the hunter will be minus 0.14 meters per second immediately after the harpoon is launched. Since the harpoon is launched to the right, from Newton's third law, the hunter and kayak move to the left. A 10 grams bullet is fired from a 3 kilogram rifle with a speed of 500 meters per second. What is the recoil speed of the rifle? Choose the rifle and the bullet as an isolated system. We apply the conservation of momentum to find the rifle's velocity. As before firing the bullet, both the rifle and the bullet were at rest, so the total momentum before firing is 0. After firing, the velocity of the bullet is 400 meters per second. The recoil velocity is minus 1.5 meters per second. The minus sign indicates that the rifle's recoil is to the left. The figure shows a space hauler and cargo module of total mass m traveling along an x-axis in deep space. They have an initial velocity of magnitude 2,100 km per hour relative to the Sun. With a small explosion, the hauler ejects the cargo module of mass 0.2 m. The hauler then travels 500 km per hour, faster than the module along the x-axis. That is, the relative speed between the hauler and the module is 500 km per hour. What then is the velocity of the hauler relative to the Sun? Because the hauler module system is an isolated system, its total linear momentum is conserved. Let capital letter M to be the total mass, space hauler plus cargo module. They have an initial velocity of magnitude 2,100 km per hour relative to the Sun. Before the ejection, the initial momentum is m times 2,100. The total linear momentum of the system after the ejection is the mass of cargo module times the velocity of the ejected module relative to the Sun, plus the mass of hauler minus the mass of cargo module times the velocity of the hauler relative to the Sun. The first term on the right is the linear momentum of the module, and the second term is that of the hauler. In this question, the velocity of the hauler relative to the Sun is required. So we should relate the velocity of a hauler relative to ejected module to the unknown velocities with the equation. In symbols, this gives us. We now apply the law of conservation of momentum. Cancel the capital letter M. Replace the velocity of a hauler relative to the Sun with the velocity of a hauler relative to module plus the velocity of a module relative to the Sun. We solve for the velocity of a module relative to the Sun. We take the equation with velocities and we solve it for the velocity required.